Okay, thanks. It's a real pleasure to be giving this giving this masterclass together with Peter about this work we've been doing, and I'm happy that all the participants. I'm happy for all the participants here. So let me switch. I've got a double camera system here. I'll switch to the paper. Is it oriented the correct way?
Yes.
Yes, okay, thanks. Right, so I'll be talking about condensed sets here. And let me just recall, Peter kind of said it, but let me recall the idea, which is that condensed sets are kind of similar, capture much of the same phenomena as topological spaces, but categorically, in terms of phenomena. But in terms of categorical properties, condensed sets are more similar to sets. So they capture topological phenomena, but their basic behavior, formal behavior, is similar to sets, which means it's easier to add on algebraic structure. So things like condensed abelian groups will be better behaved than topological abelian groups, and so on and so forth. So, okay, how are we going to achieve this? Well, so morally, well, we're going to decide that our basic building blocks will be essentially compact Hausdorff spaces, or perhaps certain specific kind of compact Hausdorff spaces. What we're going to do is, so we're going to have take these basic building blocks, compact Hausdorff spaces, and allow ourselves to glue them together, perhaps in an infinitary way, along certain relations. And the formal way to do that is, so modulo set theoretic difficulties will define a site, a notion of covering on compact Hausdorff spaces, giving a site, and then modulo set theoretic technicalities, condensed sets will be sheaves of sets.
Your camera just froze, or at least it did for me.
Oh yeah? Okay.
For me as well.
Right. Let me see what happens if I switch back to this camera. No, I can't switch back to this camera. Okay. Give me 2 seconds. Sorry about this. I have an idea. It might involve sacrificing some functionality, though. Right. Okay, I'm going to stop the video and start it again. Oh, no, that still doesn't work. Okay. I don't know what the problem is. Sorry, guys. If any Zoom people have any Zoom, well, if people who know Zoom well have any suggestions?
Try to reconnect. Try to exit and reconnect.
Exit Zoom and reconnect?
Yeah.
Okay, I'll try to do that. Thanks, Fabien.
Yes, it's now working.
Okay, hi, I'm unmuted now. So I'm gonna do it as low tech as possible now, and I apologize to everybody, but I'm gonna write on a sheet of paper and then periodically display it to you. So I've done it before and it worked, so I'll try it again. Yeah, so I'll start right now. So yes,
No.
so as you can see, we're gonna take compact house door spaces as our building block, and then we'll have a notion of covering on there, and then condensed sets will be sheaves on this site of compact house door spaces. So now let me say what the notion of covering is. So,
may I suggest an idea? How about you turn your laptop around and sort of let it film while you're writing? Is that possible?
No, not really. Yeah. I mean, I could try the same thing as I was doing before again, but I'm worried it might freeze again. Yeah, I mean,
If it freezes one more time, we can switch.
You really don't like this idea, eh? But I swear it works.
Oh, I don't know.
All right, I'll try again with the other camera. Okay, let's see here. Okay, so are we back? Oh, I have to readjust it. Oh no, it's already froze. Oh no, it already froze. What on earth? It already conked out the other one. Okay, sorry guys.
What is the other camera?
It's a Logitech Brio.
Okay, so it's directly connected. I mean, another option is, as someone already suggested, to log in with a phone and have that recorded instead.
To log in with a what? Sorry.
With a phone, with a smartphone.
Oh yeah. Mm-hmm. Yeah, I don't have
that.
Also,
I mean, I can give you mine if you want to. I don't know where you're at, but.
Let's just
Dustin, I think you
this.
should just continue this way.
Let me continue. Yeah, I'll do it this way. And
Yeah.
if there are a lot of complaints at the halfway point, then we can figure something out at the break. Okay.
Yeah.
All right. So the definition of the topology is, or the notion of covering site is that it's going to be a finitary collection covering notion. So a finite collection. So a covering collection. So we have a series of xi's mapping to y, where xi and y are all compact house door spaces, is a finite collection of compact house door spaces, mapping jointly surjectively to y. So we have to specify a collection.
both, mais bon.
So we have to specify a finite collection of, but we have to say what we consider to be a cover. And then I say that it's a covering map if just, so these are just arbitrary continuous maps and they cover if set theoretically they cover, essentially. So why this definition? So, well, whenever you're trying to decide what notion of covering you want to take, there are basically two things you have to consider, which is that you want it to be strong enough so that working locally, so that you can work locally, and that buys you something. But not too strong, meaning not too many open covers, or covers, sorry, not too strong, so that invariants you care about still are sheaves. So if you add too many covering maps, then you're just going to break apart the structure of your category. You're going to enforce too much gluing, and maybe your favorite invariants of your compact house door spaces won't satisfy the sheaf property, and you've lost track of what you originally cared about compact house door spaces. So I should explain to you why why this collection of coverings is both strong enough, but yet not too strong. I'll start with the not too strong. So why is it not too strong? Well, for example, I'm going to load up the chat. We're not losing track of point set topology. So that can be expressed as follows. If you take an arbitrary topological space Y, then if you define f of x to be the set of continuous maps from x to y, this is a sheaf. So for here, x will be a compact Hausdorff space. This is a sheaf of sets for this topology. So in terms of topological properties, I mean, the most basic kind of topological property, you're not imposing too many relations here by imposing the sheaf condition. So why is this true, by the way? Why is it true that continuous functions, so I didn't demand this be an open cover or anything like that. It's really just an arbitrary surjective map of compact Hausdorff spaces. Well, if we were looking at maps of underlying sets, this kind of sheaf condition is actually clear, because for maps of underlying sets, the sheaf condition would just be saying that maps out of X is the same thing as maps out of Y, which are constant on the fibers. That's what that equalizer condition essentially unravels to. So then you just have to see that that everything passes to continuous functions as well, which amounts to saying that if you have you have to show that a continuous function from, oh, did I have too many occurrences of Y, by the way? Yeah, I did. Sorry, my general topological space should perhaps be T. So we have a general topological space T we're taking maps to, and I want to know that if you have a surjection X to Y of compact Hausdorff spaces, then a continuous map from Y to T, a set theoretic map from Y to T is continuous if and only if it's continuous when you compose to X. And the if direction, the only if direction is clear, but for the if direction, you use the fact that a map of compact Hausdorff spaces sends closed sets to closed sets. So basically, any closed surjection is a quotient map of topological spaces. Right. But then there's another example, which Peter's going to discuss in his next couple of lectures tomorrow, is that in a suitable formulation, cohomology, sheaf cohomology of compact Hausdorff spaces also satisfies descent for this topology. That is a sheaf for this topology, this Grothendieck topology on compact Hausdorff spaces. So basically, this topology is suitable not only for sort of point set topology, but also for algebraic topology. Your invariants you know and like of compact Hausdorff spaces, both in point set topology and in algebraic topology, will satisfy descent for this topology. So we're not losing too much information when we decide to take this as our definition. Now, what about strong enough? So what exactly do we get from allowing ourselves to work locally in this very generalized sense of taking an arbitrary surjection of compact Hausdorff spaces to a given compact Hausdorff space? So this, I'll explain this by explaining a quite nice remark of Gleason, which is that the category of compact Hausdorff spaces, in a sense, has enough projectives. So let me explain what I mean by that. So projective means, so T, a compact Hausdorff space T is projective. That means if you take continuous maps from, if you have a surjection X surjecting onto Y and you have a continuous map from T to Y, then there exists a lift. So it's just what you would normally think projective means. All maps displayed being required to be continuous. And enough means for all compact Hausdorff spaces X, there exists a projective T and a surjection from T to X. Okay, so let me actually give the proof of this because it illustrates exactly the point of working with this topology. So why are there enough projectives? The claim is that if S is an arbitrary set viewed as a discrete topological space, then the Stone-Check compactification beta S is a projective object of compact Hausdorff spaces. So this beta S is notation for Stone-Check compactification of the discrete topological space S. Let me remind you one possible definition of beta S. Well, it's a space of ultrafilters, but one way of describing it is that it's the inverse limit over all surjective maps to finite sets of that finite set. So it's in essence the pro-finite completion of the set S. And this is a topological isomorphism. So this is the inverse limit topology on inverse limit of a bunch of finite sets with a discrete topology. So in particular, this is a compact Hausdorff space. And the point of the Stone-Check compactification is that it has a universal property. The continuous maps from this guy to a compact Hausdorff space are the same thing as just maps from their set as a discrete topological space to that compact Hausdorff space. So now, if we take an arbitrary surjection of compact Hausdorff spaces, we want to know that any map from beta S to Y can be lifted to X. But by the universal property, a continuous map from beta S to Y is the same thing as a set theoretic map from S to Y. And we know those lift, for example, I guess that's the axiom of choice. We know the maps of sets lift along surjections. And then that's again the same thing as a map from beta S to X. So that justifies the claim that this beta S, this profinite completion of a discrete set S, is a projective object. So now why are there enough of them? Well, actually, you can take, for any compact Hausdorff space X, you can take any set S mapping densely to X. And then by the universal property, this extends to a continuous map from the Stone-Check compactification. The image will be dense, but it'll also be closed, and then it'll have to be the whole thing. So that'll be surjective whenever S maps densely to X. And what's the easiest thing you can do? You can actually take S to be the underlying set of X with the discrete topology and take this to be the identity map. And then this is certainly fulfilled. Okay. So that explains this result of Gleason's. And what does it mean for our definition of, well, it's not the official definition because of set theoretic technicalities, but what does this imply? It means that a sheaf on compact Hausdorff spaces is uniquely determined by its restriction to, well, I'll just write beta S's, or, well, actually maybe, yeah, well, maybe I'll make this, I'll say another remark in a second. So why is this? Why is a sheaf uniquely determined by its restriction to these guys? Well, let's say we have an arbitrary compact Hausdorff space X. Then we can surject onto it from some beta S. And then our descent condition will say that we can understand what our sheaf does to X as long as we understand what it does to beta S and to the fiber product, right? Now, the fiber product is beta S cross X beta S. This is a closed subset of beta S cross beta S. And now here's a big caution. A product of projectives is not a beta S. And neither is a closed subspace. So the ideal situation would be if this guy were also a projective, and then we would understand our sheaf because we understand its value here and its value here. But this is not going to be a projective object in general. There's this really annoying technicality that these projective objects are not closed under product, which you always have to keep in mind. But it actually doesn't matter, because even if this guy isn't a projective object, it's still a compact Hausdorff space. And we can still then surject on it from another beta S prime. And then the pullback map will let us view this inside of here, the sections of our sheaf here inside of the sections of our sheaf here. And that implies that in the co-equalizer diagram, you can replace this by this at no cost. So what you'll have basically is that f of x will be the same as the equalizer of the two maps from f of beta s to f of beta s prime. And I'm glad Peter's answering all the questions. Thanks, Peter. Yeah. And so in general, if you wanted to understand some algebraic topological invariance, you'd have to continue this you'd have to iterate this and make a hypercover of your x by beta s's. And it wouldn't terminate after a finite number of steps. I think we do know that for sure, Peter, because you can take a compact Hausdorff space with cohomology living in arbitrary degrees. I mean, I'd probably want to think about it more carefully, but.
Yeah, but for a profinite set, do we know it for sure?
Oh no, but I am in the context of compact Hausdorff spaces here. But yeah, for profinite sets, maybe we don't know for sure. Yeah. Okay. Yes. So a sheaf is uniquely determined by its restriction to these beta s's, and in fact, and on the beta s's, but moreover, on the beta s's, the topology is much simpler. The sheaf condition is just the same thing as saying that if you take a beta s disjoint union beta s prime, then it's the same thing as f of beta s cross f of beta s prime. So on the level of the compact Hausdorff spaces, the sheaf condition takes two parts. And f of empty set, before Marcus chimes in, f of empty set should be a point. On the compact Hausdorff spaces, the sheaf condition would have two parts to it. One would be that it preserves finite disjoint unions, and the other would be that if you have a covering map, a single covering map, then you have this equalizer condition. But that second condition disappears on these beta s's because any surjection has a section, which renders that co-equalizer condition vacuous. So it's really just this extremely simple-minded sheaf condition that you get. Okay, I'm gonna recap this in just a second, but first I want to make a couple more remarks about these beta s's. So as far as we know, from what I've told you at least, these beta s's are just specific kinds of projective objects in compact Hausdorff spaces. But in fact, the projective compact Hausdorff spaces are exactly the retracts of beta s's. That actually follows from the fact that the beta s's are enough compact projectives. If you had another projective, you could surject from a beta s, but it would have to have a section. So it would be a retract. And these things are also called extremely disconnected compact Hausdorff spaces. So they can be characterized also purely sort of in point set topological terms in terms of their open sets. They have the following funny property. The closure of every open set is open. Yeah, don't bother thinking about it too hard. The point is, these are weird spaces. If you're trying to picture an honest topological space in some kind of a geometric manner. Yeah. They don't actually, if you've never run into one of these guys in real life, unless you built a beta S, basically. I mean, no compact Hausdorff spaces you're familiar with are extremely disconnected. for example, every extremely disconnected topological space is totally disconnected, which is the same thing as being profinite. That is a filtered inverse limit of finite discrete topological spaces. But the inclusion is very much strict. So for example, examples like the p-adic integers, which are perfectly nice profinite topological spaces, are not extremely disconnected. So in fact, essentially, we might know that you need to use the axiom of choice to produce any non-principal ultrafilter, which is the same thing as saying you need an axiom of choice to produce any point of beta S that's different from S, that's not equal to, it's not in S. So if you have any topological space where you can actually name a limit, if it's a compactification of a discrete space and you can actually name a limit point without using the axiom of choice, then it can't be extremely disconnected. These things are so free that they're just, so they basically don't show up in practice, but they're useful for us to guarantee good properties of this category of condensed sets, and that's the role they're going to play. They're going to give us projectives, which is useful for homological algebra. Okay, so now let me recap a little bit what I've just said. So we have the category of compact Hausdorff spaces, and inside there we have the beta S's, I'll call them. Or I could take all extremely disconnected ones. It doesn't, I could close up under retracts if I want. And we had our site here, our natural Grothendieck topology here, giving us the structure of a site, and it restricts to a Grothendieck topology here, but it turns out that one has a reformulation, making it very, very easy to work with. It's just the chief condition just involves finite disjoint unions. So that's very simple. On the other hand, as a category, this is it's a little less convenient than compact Hausdorff spaces, because compact Hausdorff spaces has all finite limits, for example, or even infinite limits, which is nice. So when you do constructions like fiber products, which come up a lot in this kind of theory, you're still in here, but you do leave here. As I mentioned, this important caveat that even products, let alone fiber products of beta S's are not beta S's, or even extremely disconnected. So for many purposes, it's actually useful to consider a third option which sits in between the two, which is the one that Peter actually already brought up in the first series of lectures. So that's these profinite sets, or totally disconnected compact Hausdorff spaces. We have the structure of a site on compact Hausdorff spaces, and that restricts to give a structure of a site on both of these, and they all generate the same topos. So any one of these can be taken as the defining site for condensed sets. But they all have their advantages and disadvantages. So this makes the site structure very simple, which means that these are like the most simplest kind of generators for the category. They have the fewest relations between them, essentially just these obvious disjoint union relations. Well, these ones and these ones have better closure properties. They're closed under all limits as categories. In particular, they're closed under fiber products, which is quite important. This one's closed under even more, because this is closed under quotients by equivalence relations. That's nice. This one's not. But that's maybe less important in practice, at least for what we're going to talk about. This is all, the spaces here are also a lot simpler than the spaces here, because, for example, all these spaces are zero-dimensional. So these profinite sets are all zero-dimensional, and they don't. So their usual cohomology is not very complicated. Cohomology of sheaves is extremely simple on profinite sets, whereas it can be actually quite complicated on compact Hausdorff spaces. So this is actually kind of a nice middle ground. It has good categorical properties, but the basic objects are not too complicated. And you can often argue by reduction to the case of finite sets here, or make constructions by reduction to the case of finite sets here. So that's why maybe this is the preferred site, although for many arguments, you want to use this one here. And actually, I don't know any arguments where it's important to really use this one. So maybe it's the most geometrically clear one, but actually we're probably going to stick to this world from now on, or either of these two worlds from now on. Okay, so I'm going to now go and the next thing I'm going to do is get into a little bit of the the set theoretic technicalities, and then explain. And then I want to be able to explain why we have such good categorical properties for condensed sets. Why exactly they are very similar to the category of sets. But maybe I should stop here and ask if there are any questions about the things I've already explained. No, excellent. Okay, so we want to define that the category of condensed sets is the category of sheaves on, say, profinite sets with this Grothendieck topology of finitely many jointly surjective maps. But we can't. We're not allowed. Because profinite sets is not a small category. Which means, so what is a sheaf category? Yeah, basically another way of looking at it is, you know, okay, it's a certain sheaf condition is a certain condition on pre-sheaves, and pre-sheaf category is generated under colimits from the representable pre-sheaves, which are the objects of the site you started with, and that passes through the localization from pre-sheaves to sheaves. So every sheaf category is generated under colimits by the defining site, but then there are certain relations between these colimits coming from the Grothendieck topology. But when you have it, if your category was too big, then you would be allowing yourself to have sheaves which are generated by more than a set's worth of objects. And this would mean that your mapping sets, your Hom sets in your category would be things, will be limits of things along non-sets. I don't know, or if you just look at the definition of a Hom set in a functor category, I guess I'm saying if the source category is not small, then you're taking a limit over a set that's not small, and so it's not small. Okay, I feel like I didn't explain that very well, but the reason you're not allowed to do that is because then the Hom sets would not be sets. Right.
Well, maybe that's a question that you want to answer.
Okay.
Why do we take only compact Hausdorff spaces and not all topological spaces or something like this?
That's a very good question. Yeah, so I just said our building blocks were going to be compact Hausdorff spaces, but I didn't say why. The reason why we don't take more is because basically all the topological spaces you encounter in practice are so-called compactly generated, which means they're sort of formally determined by their compact Hausdorff subspaces. So a set will be open if and only if its intersection with every compact Hausdorff subspace is open. We'll get into this a little bit more later, but that's true of basically all topological spaces. And that's going to imply that these compactly generated topological spaces embed fully faithful already in this pre-sheaf category of compact Hausdorff spaces. So you don't need to throw in more in order to get the examples that you want. But on the other hand, we can actually control these compact Hausdorff spaces fairly well, because in the profinite perspective, for example, they're just built from finite sets in a certain reasonable way. Yeah. Right, so the Hom sets are not sets, which is bad, and there's only one way to fix this, at least at first pass. So we need to consider a truncated version of compact Hausdorff spaces where we bound the cardinality. So am I saying that for a suitable topology on C? Yes, I am saying that, Adrien. Yeah, I'm precisely saying that. Yeah. Right, so about what kind of cardinality bound do we want to impose? Well, we would still very much like to be able to do this procedure of switching between compact Hausdorff spaces and extremely disconnected compact Hausdorff spaces, or these beta S's. And in there, we had to pass from X to the underlying, the Stone-Check compactification of the underlying discrete set of X. Okay, but the Stone-Check compactification is yeah, you can think of it, the ultrafilters is a set of subsets of the power set of S. Yeah, so we have to iterate power set operation twice, basically, in order to get from X to its compact projective cover, but then you'd want things at that set theoretic level also to have covers. Anyway, the definition we're going to want to employ here is that a cardinal is a strong limit cardinal if and only if, well, whenever you have lambda less than kappa, this implies that 2 to the lambda is also less than kappa. So in other words, the power set of any k small on any kappa small set is still kappa small. Okay. So one example would be aleph naught. So because if you have any finite set, then its set of subsets is also finite. But actually, there are many more examples. It's easy to make examples. Not the same site. I'm sorry. Yes, the same topos. Yeah. It's easy to make examples of these guys. So there's this thing called the Beth hierarchy. So you can define by and now I don't know how to draw Hebrew letters very well. I'm not very practiced in it. Oh boy. I don't even remember which direction the boxes go. Well, anyway, maybe I won't try to write it down then. Thanks, Tomar. Yeah,
It's
much appreciated.
it's a mirror image of a C.
Okay. Yeah.
Basically.
So we have this.
More like rectangular.
Yeah. So you can define by transfinite induction a function from ordinals to cardinals called the Beth function. So you take Beth 0 to be I don't know, the one element set. I don't know what the right initial datum is. And then for a limit ordinal, you take Beth alpha plus 1 to be 2 to the Beth alpha. So you take the power set of the previous guy. And then for a limit ordinal, oh sorry, yeah, first, what did I say? For not a limit ordinal, if the ordinal has a successor. And then if you have a limit ordinal, you take the union of all the previous ones. So alpha prime less than alpha of Beth alpha prime. So so if you've got a successor, then if you have a predecessor, then your Beth of the guy is the power set of the Beth of the previous guy. And then if you're a limit ordinal, then you take the union of the previous Beths. And then for a limit ordinal, in this case, here, this will be a strong limit cardinal. Yeah. So the first strong limit cardinal you might want to consider. Well, I guess depending on your conventions, maybe aleph naught is also aleph naught is a strong limit cardinal. But the next one after that will be Beth aleph naught, which will be for all practical purposes. You can just take kappa to be Beth aleph naught. I don't know anything that we do with condensed sets that wouldn't work with sheaves on kappa small compact Hausdorff spaces for this specific choice of kappa. Right, so then, well, let me just make the definition. So the category of kappa condensed sets is sheaves on kappa small, well, either beta S's or profinite sets or compact Hausdorff spaces. So we bound the cardinalities of the basic building objects. Now, in any sheaf category, you're allowed to take arbitrary colimits, small colimits of your building objects, and we're not bounding the cardinality of the colimits, right? So the colimits are still as large as you want, as long as they're small. I mean, as long as it's indexed by a set. But the basic building blocks we're bounding the cardinality of. Yeah, and so that's for a strong limit cardinal kappa. So you could just fix such a kappa and work with this, and everything basically we say is going to be true. I mean, you might have to check some certain details at some point to make sure things are still kappa small and so on and whatever, but everything's going to work just fine. So if you're willing to ignore technicalities, then yeah, everything's cool. So let me, but you might not like this having to choose a cutoff cardinal cap. Well, maybe I should mention, so Barwick and Hain, they've been doing basically the same thing as us at the same time. And I'm going to mention the difference between what we do and what they do, but it's not to emphasize the difference in any way. I mean, the difference is purely cosmetic, how you resolve these set theoretic technicalities, essentially. The core of the theory is the same. We're doing the same thing as them. They're doing the same thing as us. There's no real difference. But I just want to, but since we're talking about set theoretic technicalities, I'll mention what they do. So they actually choose kappa to be a strongly inaccessible cardinal. They want to allow a lot of freedom to expand their basic building blocks. So that means it's not just a strong limit cardinal, but it's also a regular cardinal. So a union of things, a kappa small union of kappa small sets is still kappa small. And if you're a strongly inaccessible cardinal, that means basically that the kappa small sets are closed under all set theoretic operations that you can conceive of, because they're closed under both power sets and kappa small unions. So it's a so-called Grothendieck universe, a place where you can just do your set theory as if you were working in ambient ZFC. So they make that choice. On the other hand, I'm not sure in any mathematical argument that there's a reason to require kappa to be strongly inaccessible and not merely a strong limit cardinal. And to produce strongly inaccessible ones, you do need axioms beyond ZFC. So I'm not so sure from a mathematical argument perspective that it's necessary to make that restriction. But what we do in the condensed approach, we take the union over all kappa of sheaves on kappa small. Well, I'll just write beta S's. So I'll explain union along what in just a second. But basically we want to say, okay, so maybe, I mean, a condensed set is basically you build some object formally out of colimits of a compact Hausdorff things. And now we're just saying basically, where's this? Yeah, maybe I'll make some comments. So, right. So let me explain what I mean by this union. So if kappa is less than kappa prime, there is a pullback functor. From kappa small beta S's or compact Hausdorff spaces or whatever to kappa prime small beta S's given by the inclusion, the fully faithful inclusion. So by saying there's a pullback functor, I mean we have a morphism of sites in the opposite direction in the sense that Peter described in his notes. But this gives then a pullback functor from kappa condensed sets to kappa prime condensed sets. And this is also fully faithful. And how can you describe this functor explicitly if you just unwind the definition of a pullback functor on maps of sheaves, on categories of sheaves? This sends X to the functor. So your compact Hausdorff space, or T will map to the colimit overall T maps to T prime, where T prime is kappa small of X of T prime. So you have your kappa small condensed set, which is a particular kind of pre-sheaf on kappa small compact Hausdorff spaces or profinite sets or so on. And you want to extend it to all guys, and you just say, okay, you just formally demand that, well, I don't know, it has to come from its values on the smaller guys. And this formula is designed so that if you take a representable guy, it gets sent to the corresponding representable guy here. That's how it's designed.
I don't think you need to sheafify this, by the way.
No. Well, it depends on which defining site you choose. Yeah, I was just going to make that comment. So, yeah, in fact, I'm going to get rid of that sheafification. That sheafification is necessary if you take compact Hausdorff spaces or profinite sets, but it's not necessary if you use this extremely simple, extremely disconnected basic building block. In fact,
do you actually need it for? a profinite set?
Well, let me put it this way. I can make an argument in the extremely disconnected case, and I don't know, maybe you do, but I don't know how to make an argument in the other two cases.
I mean, for compact Hausdorff, I wouldn't be sure, but I thought I once checked the works for profinite sets, but I'm okay. No guarantees.
Okay. Yeah, I mean, I wouldn't. Yeah, I have no. Yeah. Okay. I want to extricate myself from this set theory discussion. Right. So what kind of things do you need to check to be careful? Right. So what do we need to check? Well, we need to check. So we'd like to work with condensed sets as if it were a topos, right? So we'd like to be able to do all of our usual categorical operations on condensed sets and have them still be condensed sets. But we don't know that we can do that yet. We just made this definition of a filtered colimit of topoi. So if we have a bunch of objects, well, we can put them all in one finite stage and do whatever operation we're thinking of there. But we have to know that if you change kappa, so if you make kappa bigger, or at least if you make kappa big enough, then yeah, or at least after a certain point, you know, that your operation stabilizes. Like for example, let's say you have a diagram of condensed sets, right? A small diagram of condensed sets, and you're interested in taking its limit. It's not clear a priori that this limit exists as a condensed set. So it's some pre-sheaf on compact Hausdorff spaces or whatever, but why should it satisfy the sheaf condition? So what you can do is you can put, but certainly you can make, you can put these all in some, they're all kappa, you can put, since it's a small diagram.
It's clear it satisfies the sheaf condition.
Oh, sorry. Yeah, no, not the sheaf condition. Thank you, Peter. My mouth is moving without my brain being involved. It needs to satisfy this. It needs to still be a small colimit of representables. Basically, is the condition to be a condensed set. Right. So how do we check that? Right. So you have to argue. So you put your diagram into some kappa kappa condensed sets. There it is a topos, so you know the limit exists and is what you want it to be. But then you have to argue that when you make kappa bigger, or at least if you make kappa big enough, then the limit stabilizes. So there's going to be a comparison map between the limits in the kappa world and the kappa prime world. And you have to check that when you increase kappa enough, eventually that stabilizes, and then that limiting value will be the limit of your diagram in condensed sets, and you will have proved that condensed sets contains all limits. And you can do all of these kinds of things by analyzing this formula here. So essentially, when you make kappa big enough, this colimit will be really, really, really filtered. And then it'll commute with bigger and more kinds of limits. But you do have to do some slightly annoying set theory arguments to check that. You can find that one in Peter's notes. And I was going to give a little more detailed version of such an argument, but I guess I only have 10 minutes left in this lecture, so I'd rather well, we'll see. Okay. Right. So I do want to make a remark. There's an alternative definition. Of condensed sets. Based on the beta S perspective. Right, so first of all, for kappa condensed sets, so while the claim is that condensed sets, if you view it as a, I'll speak very loosely here and say we view it as a full subcategory of the pre-sheaf category on all beta S's. Of course, this is not a category, so the home sets are not small here, but they are small here. So permit me this slight imprecision of pretending this is a real category for a second. But this is the full subcategory spanned by the sifted colimits of the representables. So this is a quite interesting thing, which is unusual for toposes, I guess. that you can express the sheaf condition. So the pre-sheaf is basically all colimits of representables. But it turns out this sheaf condition is the same thing as just picking out certain colimits of those representables, namely the sifted colimits, which came up in Peter's previous talk. So these are the things which are a combination of filtered colimits and reflective equalizers. Right. And from this, so the way you prove this is basically you do it at the kappa level and then you take the union. But this gives another perspective on what a condensed set is, because these sifted colimits, it's kind of generalized, or these reflexive coequalizers, at least, it's kind of a generalization of notion of a presentation of something in algebra. Yeah, so if you have a group, you can present it by generators and relations, and that always gives a reflexive coequalizer. You can always build that with a reflexive coequalizer diagram, and that's, yeah. And then you also can add filtered colimits if you want to be able to make things bigger, and not just take quotients. Yeah, so you can think of kind of, yeah, I don't know. So in some sense, condensed sets are the kinds of things that can be built using projective resolutions based on extremely disconnected things, beta S's. Right, so, but anyway, the upshot is that condensed sets satisfies all the axioms satisfies all of Giraud's axioms, except existence of a small generating category. But it has also all the same closure properties, like limits exist, internal Homs exist. So let me remind you that, Giraud's axioms basically say that finite limits and arbitrary colimits interact exactly like in sets. So that's the first thing I want to say, is that as in sets. And the second thing I want to say is that arbitrary limits and sifted colimits are also exactly as in sets. So this is some topos thing, and this is some algebraic theory thing. So I'll make some more comments. Right. So general topos behavior is that finite limits interact with arbitrary colimits exactly as in sets. So this is why, for example, in the abelian sheaves on a site, your filtered colimits are act. Yeah. So the kernel, you can take kernels and infinite direct sums interact just like in abelian groups. And it's responsible for other things like that. This sifted colimits and arbitrary limits interacting exactly as in sets. This is very much not a general topos thing. This is more an algebraic theory thing. So this is satisfied in examples like groups, abelian, groups, rings, whatever you like, stuff like that has this property. And that comes from this, this comes from these compact projective generators, which Peter talked about. So if you take T to be extremely disconnected, then Hom from T, if you as a map from condensed sets to sets. So these, if you take T-valued points on any condensed set, that commutes with sifted colimits and arbitrary. Well, essentially because of this very simple nature of the topology on T and arbitrary limits. Well, because it's a map, and this and these guys generate the topos since they form a defining site, and therefore you can test anything just on T-valued points, and that will tell you that you can reduce such interactions to the case of sets. Right. So I've got 5 minutes left. What to say? Oh, I think actually, yeah. should I give an argument for something? So I mean, I intended to use this first lecture to explain that the category of condensed sets is very similar to the category of sets, and I feel like I did that a little bit, or this is what I was trying to end up with. But I did skip a lot of arguments. Is there something that anyone is particularly interested in seeing the details of? Oh no, okay, maybe, sorry for putting you guys on the spot there. Maybe I can think of something to say, okay? Let's pass to condensed abelian groups. So what is a condensed abelian group? Well, there are two ways of defining it. This is either, well, and they're equivalent, yeah? It's either an abelian group object in condensed sets, or it's this same as condensed sets, but with sheaves of abelian groups. And that's it's pretty clear that you get the same thing in both cases. So then this is an abelian category. Is a Grothendieck abelian category. And a special case of what I said is then that, well, in an abelian category, you know, the finite limits and finite colimits are the same. They're both direct sums. And so sifted colimits are only finite colimit away from being arbitrary colimits, if that makes sense. And so what you deduce is that arbitrary limits and arbitrary colimits interact exactly as in abelian groups. Interact exactly as in abelian groups. So for example, infinite direct sums are exact, but also infinite direct products are exact, which is quite special for a sheaf category and comes from these compact projective generators. Yeah, I guess those are the two basic ones. In fact, condensed abelian groups is an example of an abelian category with enough compact projectives. So a compact projective means that Hom out of M from your abelian category A to abelian groups commutes with all colimits. And enough means that for all M in A, there exists a compact projective pi in A, and a surjective or an empimorphism from the direct sum of the pi to M. So in our case, we can take the compact projectives to be the free condensed abelian groups on the beta S's. These provide enough compact projective generators, essentially by construction. And this is what we're going to be using a lot to do calculations and so on, is these compact projective generators for the category. They make the homological algebra very simple. So let me make a remark. An abelian category with enough compact projectives, well, which is in fact generated by a single compact projective, This is exactly the same thing as a module over a ring. So this is the most usual, most nicely behaved setting for homological algebra. So if you have a single compact projective generator, it's essentially by Morita theory. The abelian category has to be the category of modules over the ring. Well, I should maybe say a Grothendieck abelian category. I mean, I don't need to say that, or just enough co-limits, basically. I want it to be co-complete. That's probably enough. Yeah, that has to be modules over a ring. And so this is just a slight generalization of the notion of this abelian categories with enough compact projectives. It's a slight generalization of the notion of category of modules over a ring, where you're not generated by just one object, but by a whole set's worth of objects, or actually in our case, a proper class worth of objects. But in terms of the formal categorical properties, it's just like working in mod R, basically. And that's what's going to make everything nice and smooth for us. So yeah, when we get back from the break, I guess in 15 minutes, I'll then explain the other half of the story, which is why these condensed sets are capturing topological phenomena.
Okay, thank you, Dustin. So